Oh yeah.
It felt good when it's happening.
You okay, Leo?
Yeah.
You should not.
Nah. The food was good when I saw the pizza. Okay. So, yeah,
We're not there.
just throw it out. That's the easiest way.
Yeah.
I agree.
Your eyes.
All the time. Yeah.
I mean, if you're not doing like, I don't know, like clothes and stuff, like, what are you doing yourself? Yeah, but you don't like, that's like different. That's, you guys are doing like meetings, like I have like people that I actually have to like say like, hey, you guys can do this week. Because Jacob just, I want to do a talk next semester.
It's basically on the list. So immediately understand the tech. It's like I'm Catholic. Yeah, perfect.
I want to give you as much of burden
Yeah, I only.
I know one of her.
I asked
I feel like I union. I would actually write. Russ, on the other hand, when I'm Russ, starting from one kind of part.
Yeah, there's no option called here.
Not really.
Classic English.
I'm taking the trifecta and 365.
You got it. You can do this kind of thing.
Okay, Biz, Matthew,
Drinka,
what?
which Matthew?
Matthew Bergsteiger. Okay. These are some of the people whose faces I haven't completely. Cristobal. Rider Rod. Derek She. Cameron Wooler. Andrew I am not sure what happened.
So I have actually one of the plans.
Okay, so what the names is, let's see. So the last class, and I asked whether people wanted to have an open question and answer session, or you want me to give a lecture. And apparently 87% wanted me to talk. The innocent and ignorant TAs thought that meant that the students really love to hear me. But you and I know what really that means. You don't want to think and ask questions. It's better for me to talk. So that's what I think we'll be doing. So essentially, there's a bunch of things we will do. Actually, I just added this just for the fun of heck of it, because it's a paper to be presented. It's an outstanding paper, award-winning paper that's going to be presented at NeurIPS next week. NeurIPS is one of the bigger AI conferences, and what they're talking about is connected to things that we have done, obviously. So I'm going to just sort of give you a little connection to that, and then we will talk about completing as much as I can of the Bayes networks learning. It may well be that for this part, I'll only do a very quick run through, and then that's Cameron, I know that. Some people I still know because the haircuts are different enough that you can figure out even with the masks. But anyway, by the way, that's the other thing, that we actually completed an entire semester with masks. And some of you I have gone to lunches with, and so there you had to remove your mask to eat. And it was very interesting exercise, because it turns out that we all, like generative adversarial networks, complete what we are not seeing. So I have actually completed various people, without having seen them, because I mean, your mugshots are worse than the jail mugshots, so I can't actually tell who is who from that. And it turned out that when they actually removed the mask, it was very interesting that it's not that one is better or worse, it's just I completed it wrong, because there are infinite ways of completing the remaining pixels. And I did one based on my biases, and that just didn't work out. So it is very much possible that if we cross, especially those of you who haven't had lunch with me, if we cross paths and you say hello, I'll say, and then you just put on your mask, even if it's 20 years later, and then I'll recognize you. Okay. Anyway, so that's good. Actually, we actually completed an entire semester with masks, I guess. So as I said, the incomplete data and EM algorithm is actually, it almost takes a one full class, and I just don't have that, unfortunately. So I'm going to kind of get you to understand what happens there, and I'm more likely than not going to give you a lecture which discusses the stuff more at a leisurely pace. In fact, EM is actually a great algorithm. It makes connections to all sorts of things. So it is worth knowing it. But no, there's a timing constraints. And then I think the last 15 minutes, I sort of provide some sort of a summary review of the course, so that you'd feel as if we didn't just end mid-sentence. Okay, that's what we're going to do. As far as the exams are concerned, I'm going to send you more details on Piazza. But approximately what we expect you will have to do for the final exam is there will be two different parts. One would be a set of true-false questions, and depending on how we make you do that, if we make you do it just by giving true-false without justification, we will have negative marking for it. And if we also ask you for justification, then it's just based on the justification. So, but that would be for the entire semester. It'll be a bunch of true false statements about the entire semester. And then there will be a written part, the specifics I haven't completely decided, but it would be only focusing mostly on the stuff that wasn't covered in the first two exams, which basically means base nets and base net learning. Okay, and everything will be, neither of them will be in class. So you don't actually have to see me after this. But we will basically, again, the same expectations apply, that you're all honorable people, that you're going to have to kind of, certify that, that you have basically followed all the rules. Okay. Any questions on that? Okay. So that's regarding that. So I put myself an alarm for like 2:20 to shift to the summary part, but let's just see how far we go before that. So as I said, this one I just added, it was really not part of your course, clearly, because it's a paper that's coming up next week. But that's kind of one of the fun parts of being in areas which are, parts of which are still evolving. And so the point here essentially is, I just want to remind you that we talked about this issue in statistics where if you have a bunch of data points, and if you put like the simplest polynomial that goes through it, you are better off than if you put a polynomial with huge number of coefficients. The coefficients of the polynomial can be thought of as the parameters of a network. You understand what I'm saying? So function size is based on how many parameters are there in defining that function. Okay, so we kind of talked about the fact that in statistics, basically there is this expectation of bias variance trade-off, that as you keep reducing the training error, the test error first reduces and then starts increasing. Okay, and that in fact, if you have too many parameters, that if you're trying to fit the data with a very high capacity function basically means very high order polynomial. Think about it that. Okay, then a very high order polynomial can go through any set of training data points, and it will make the error zero, right? And the problem, of course, is it's overfitting in the sense that it's sort of getting used to the peculiarities of the training data, but it's not going to be able to generalize to the unseen data. Okay, so it's expected that if you are using the number of parameters that's more than the number of data samples, then maybe you are in the over parameterization regime. That means you have, let's say, 100 data points, and you're using 120 parameters for a function. Then in essentially, the function can just basically go through the entire data. And that is not going to be generalizing well. Now, when you think about generalization for functions, one of the things you have to think about is, suppose I gave you some points. There are, you can see that, right? So there are things like this part. We don't know what the function is in those places, right? Those are called interpolation points. So if you learn a function, then you are interpolating between the points. You guys get that? Yeah. But I also did not tell you what happens anywhere in this whole area with the function. That part is called extrapolation. You guys understand that? So there are two kinds of, when we talk about generalization, if you think of generalization in terms of function curves, then you can think in terms of interpolation generalization and extrapolation generalization. Okay, and in general, when we were talking about these kinds of things here, they were talking about the fact that the interpolation might be becoming too crinkly. It's not smooth if you have too many parameters. Much of this should be sort of repetition for what we've been talking about this whole semester. Now, we then found that in the case of neural networks, actually, the number of data points and the number of parameters are, number of data points is, let's say, 100, number of parameters tends to be 1,000. See what I'm saying? In the case of ImageNet, they had about, let's say, thousands of images during the ImageNet training original time, and they had 500,000 parameters. And then people were always worried as to why is this working at all, because it should be over parameterized. And then we brought this up, and I mentioned this. How many of you remember this? Actually, some of you remember this because you wrote this in your reflections. This is a double descent thing, where we basically argued that, well, it seems to be, I kind of told you what the current understanding is, that what is happening here is when the training error becomes 0, that means by this time, the function has actually gone through all the data points exactly. Or if it is a classification scenario, it classified all the training data correctly. So the training error itself is 0. And then you continued still adding more parameters and training it. At that point, what is meant by training in that case is that there is no training error, right? Remember, the backpropagation is the signal for backpropagation comes from the error. If the training error is 0, then there is no signal. What was the signal that was coming still beyond the training error becoming 0? You guys remember? Yes, what? What? Regularization. So there you are basically adding some constraint on the weights, for example. It's kind of connected to what we were discussing last class about Bayesian learning, where there are certain kinds of hypotheses have higher probability than certain other kinds of hypotheses. Certain kinds of functions you think have higher probability, higher likelihood of being good functions than other kinds of functions. And this regularization constraint was trying to catch that. And it is that regularization constraint that is still non-zero. And you can keep on essentially training. And we did basically say that what is happening in that case is the function becomes smoother beyond this, 10, whatever the training points. If you keep increasing the parameters, the function is becoming smoother. And that's what is happening. And so we also this position of double descent, that if you keep doing it, in essence, you may temporarily, in some cases, see the training test error increase, but then again come down, and it will come down more than it was before. It was still, the whole thing was a bit of a mystery, and we still are going to be in a bit of mystery. But this new paper that is going to be presented next week, essentially, and this essentially shows that we have it all backwards, and that really you should be surprised that the ImageNet networks are really only using 500,000 parameters. If you want the functions to be smooth, remember the smoothness basically means there is you have to define mathematically what the smoothness is, but you currently have some intuition. I'll define the mathematics in a minute. Okay? So the smoothness of the function, if you have put some constraint on how smooth the function should be in terms of the interpolation, that constraint to ensure that any function that ensures both the smoothness and the training error being 0 will require parameters that is of the order of number of data points times the dimensionality of the data. Okay. Now, if it's a 256 by 256 image, that is 256 times 256 pixels. That is 65,000 dimensions. When people talk about high dimensions, that's what they mean. Whereas when you're drawing, pictures of this kind, you're talking about essentially one-dimensional data. X is 1 point, and then Y, for every value of X, there is a Y value of 5. You talk about multivariable calculus, but even physics only uses multivariable calculus of 3 variables because 3 dimensions. If you're into big time string theory, maybe 17 dimensions. Data science has no end to the number of dimensions. You guys get this, right? So essentially, they're basically pointing out that by that calculation, and they have, the proof is, of course, the reason the paper got all that interesting, all that recognition. But the take-home message is that by that analysis, you would need about 10 billion parameters to do smooth interpolation on the ImageNet data. So you're barking up the wrong tree. You should have been saying, how the heck are we getting anywhere with so few parameters? As again as saying, why are there so many parameters? You understand what I'm saying? It's worth bringing up because it's sort of anything that changes your mindset is useful to understand. Okay. So that's basically is what that this paper is. You guys can look it up if you want. Universal Law of Robustness. And it basically got an outstanding paper award, one of the outstanding paper awards in NeurIPS. It will be presented on Tuesday. Now, what I want to show you is a little bit more about what is going on here. To understand the smoothness, some of you are from math, so you probably understand how to define the smoothness of a function. Basically, the smoothness of the function is defined in these ways. That is, between the function's value between 2 very nearby points, x1 and x2, would not change more than k times the difference between x1 and x2. That's what we typically mean by smoothness. For small changes in the data, there should not be big changes in the function value. Right? Except you can actually, there is this idea called Lipschitz smoothness. And what that basically tries to do is actually to consider what is the constant k, such that for every point, every pair of points on that function, f of x1 minus f of x2 will always be less than or equal to k times that x1 minus x2. What's the smallest such constant? That's called typically the Lipschitz constant of the function. And the smaller that constant, the more smooth the function is. You guys see that? Because that basically you're saying if k equal to 1, that means if you change x1 by epsilon, the functional value cannot change by more than epsilon. Just for 1 second, just in case whether we are, are the things like threshold functions, are they smooth by this definition? They are not. Threshold functions are not, because in a very small region, they change value significantly. But if you think that there is a high dimensional function over the image points, and again, here's the problem. You're thinking of image points means you're thinking of a 65,000 dimensional space. Can you visualize it? Any of you? You can't visualize more than 3 dimensions. Some of us have trouble visualizing 3 dimensions. Mental rotation is a huge, big problem for some people. But what happens is that we think that since we know 1 dimensions and 2 dimensions and barely 3 dimensions, anything that works out there will also be true in the high dimensions. And I already shown you during the class that that's actually barely true. Because if you got a 10,000 dimensional apple and you peeled it, you have no apple left. Remember this? Right? Because r minus epsilon by r power n, where n tends to infinity, is going to be 0. You can see the math, but does that mean that you have the intuition? Of course not. Similarly, you think that lines, connecting points in small dimensions are smooth. But low order things connecting high dimensional points may still lead to functions that are actually non-smooth. And so the math basically here says, by the way, this animation just shows that for a Lipschitz smooth function, there's always a cone such that if the cone is whose origin is being taken over the function will always be outside of the cone. So that means it's not making big jump and suddenly going inside the cone. The wider the cone is, the smoother the function. The narrower the cone is, the less smooth the function. And so the interesting point is that we are kind of making the assumption that if you're looking for smooth functions that go through these data points, then you can show that you would need n times d weights, parameters at a minimum, where n is the number of data points and d is the dimensionality of the data point. And this is something that we should have thought of before too, because saying that there are 5 data points of 1 dimension each is different from saying I have 5 images of 65,000 dimensions each. Okay. And so I think the big reason here is typically it becomes surprising to us. Mostly, this is what I was writing yesterday, because people tend to think, I mean, to the extent it is surprising to us, it is because we tend to think that what works in low dimensions works in high dimensions. There are at least 2 things you knew that are not true like that. For example, the high dimensional apple. The other one, by the way, is this thing I wrote, which is in high dimensions, having completely closed minima is extremely hard. You already see that in 3 dimensions. In 3 dimensions, you can have a hanging valley, which is sort of like a minimum, but you can come out this side. This is what I'm saying. So gradient descent will get stuck normally in local minima. And people assume that you have high dimensions, even more local minima, and so it should get stuck even more. Maybe it is, but there is also reason to believe that there are actually much fewer local minima than you would expect in high dimensions. Because actually constructing a local minimum is very hard in high dimensions because it has to be closed in all dimensions. It has to be closed in 65,000 dimensions in the ImageNet. Now, this is basically about math. It has nothing to do with AI by now. So what math is saying is if you want smooth functions, then you shouldn't be surprised that you need these many parameters. You should actually be surprised that you're getting by with so few parameters. Now, the different question is, why do we think smoothness would be connected to the right generalizability? That again goes back to the Bayesian prior business. We tend to assume that smooth functions must have been prevalent most of the places. If they weren't, maybe we won't be here. Imagine that very minor changes in the face, all of you have mugshots. If I change like 3-4 pixels on one of the pictures, then this guy becomes this person. You understand what I'm saying? That would be a very non-smooth thing. But in such a world, we probably would have been dead by now. Because, tigers and people might start looking very similar because there's very, very minor differences in terms of, with our visual setup, we can't tell the difference in just a couple of pixel difference. This also explains what was happening, and all of you are very, very interested in based on what you're writing about the school bus ostrich, where you thought it was still a school bus. The second one is a school bus, but the second one has slightly different pixels than the first one. You have bad eyes, so they can't tell the difference. Good for you that the real world is the world you live in is such that an ostrich looks considerably more like an ostrich than a school bus. If you were living in a world with your current set of eyes, where minor changes in the pixels will change the entire class, then you'd have been eaten by the nearest tiger or fallen under the nearest ostrich. So that's why we are expecting smoothness. And then these guys are saying, you want smoothness, you need to pay. Yes.
Do different functions want different levels of smoothness, or is there one?
So this paper, by the way, you guys, if you are into, those of you with some math background should read this paper. This paper very nicely, quickly gets into I mean, it's all, they built on some of the work that they've done before, and they essentially come up with a minimum Lipschitz constant that needs to be there to avoid getting fit to noise.
That's something that works for most of them.
That's basically the reason they're getting the outstanding paper award. Okay, but it's a great paper, but I think more importantly, it also has an interesting connection to the kinds of things that you're doing here, which is we can't just count the number of data points. You need to count the data points and the dimensionality of the data. In fact, I don't know whether I did it this time, but one other time when I did this whole discussion, I make this distinction between low dimensional versus high dimensional learning. And the only difference really is learning doesn't change. Your intuitions are right for low dimensions, wrong for high dimensions. And so data science people really, on one hand, are not exactly physicists doing string theory, but on the other hand, way more complex problem than string theory. Because any arbitrary data, image data might have thousands and thousands of dimensions. That's a much, much harder thing to have intuitions about. The math works, but it's you who doesn't work because you're expecting something else to happen. You guys understand that? Okay, I thought it's worth bringing it up. Yes.
I think if it says like it's so many like so many parameters once you get like more dimensionality, more data points. Is it like something that's like computationally viable for us to do with like these kinds of networks, or is it something that like,
No. There are different issues in terms of actually nobody has. In fact, these guys end the paper by saying it would be good if somebody. I mean, these guys are a bunch of two mathematicians, a grad student and recently grad student. Okay, and they probably touched computer probably to write the LaTeX formulas. I mean, I can't make up this stuff, but so they basically just said, given our theorems, somebody should basically take the time to train a 10 billion parameter network on the ImageNet and see what its properties would be. So you could do that, and of course, it would be computationally costly. But again, the question is, what did we expect? Previously, you're expecting you're already using too many parameters. Now you know that you're not using enough parameters, so you expect to pay the price, which is a very different mindset in terms of understanding what's happening. Okay? Yes.
Isn't using more parameters against the concept of generalization?
That was the whole discussion. What I was talking about essentially is the generalization really is, this is the part that's kind of hard to get intuitions about because you don't have intuitions about this, okay? There are two kinds of generalizations in functions. One is interpolation, one is extrapolation. Nobody really knows anything about extrapolation. Interpolation between going from this point to this point is the function too crinkly. That's really all you mean by generalization. Because the word generalization doesn't have any mathematical meaning. If your world is made up of smooth functions, and if you learn smooth functions, then you would generalize correctly. If on the other hand, you are in a different world which is made up of very crinkly functions, making smooth functions will make your performance bad. Again, this brings up this issue of generalization depends on what you think the world is like. The Bayesian learning, the prior hypothesis probabilities, the minimum description length principle, that things that can be said in fewer terms typically are likely to be more higher probability in terms of prior hypothesis probability. All of these are meta assumptions about what you think the world is like. There is no name, there is no mathematical concept called generalizability. Everybody has a pet theorem. Smoothness means generalizability. Then I'll work on smoothness, which many people were doing. And these guys said, if you're going to do on smoothness being generalizability, this is what you should expect. You shouldn't keep saying smoothness is generalizability. Oh my God, why am I using these many parameters? They're saying really, you should be thinking, why am I stopping at 500K when I should be going to 10 billion? Mind blowing. But mind blowing in a wrong way, which is you wrongly transported nonsensical lower dimensional intuitions to higher dimensions without having any actual reason to do so. In fact, I say this here, and I don't want to go into it too much now, but so I talk about even if you have 2D data, right? It turns out that naturally occurring, if you're trying to make naturally occurring landscapes, like mountainous landscapes, then a mountainous landscape, X and Y is the coordinate, Z is the altitude. So for a particular mountainous landscape, I took like 100 or 1,000 data points. X1, Y1, here is the Z1. X2, Y2, here is the Z2. X3, Y3, here is the Z3. Now you're supposed to make it into an actual realistic looking mountain landscape. The simplest would be kind of connecting them by hyperplanes, piecewise planar. If you do that, it would look like some kind of a crystalline landscape, which doesn't actually exist in the real world. That's just a kind of an intuition I'm trying to give you, but that's basically what I'm trying to say is that you don't have a good notion of what smoothness is in high dimensions. You think that it'll look like the picture that we drew in the one dimension, but really all that works is the map. Okay. Any questions on that? This was supposed to be a 5-minute discussion, digression, so I guess we are very much at time. So I think we have even less time than I expected. So I'll basically only do the parameter learning part before shifting to the review, I guess. So the parameter, we started talking about the Bayes network parameters learning, right? And I pointed out that you write if it is a very simple network like this, essentially it's just a network with one node and it has a prior probability theta. And then if I see a bunch of data, then I can compute the likelihood of each data point. And since all the data is independent, given the hypothesis, I can multiply those hypotheses, those likelihoods. And since I have likelihoods being multiplied, I can take a log of it and then maximize it with respect to theta. If you do that, then essentially that's what maximum likelihood estimation of the Bayes network parameters. And it turns out that doing it by the calculus way does exactly what you think would have happened intuitively, which is you would have taken essentially the number of cherries by total number of candies. Is the cherry problem. Okay. But then, and then I also mentioned quickly, and that for the multi-parameter case too, it's the same exact idea, except in the case of single parameter case, you take derivatives. In the multi-parameter case, you will have to take partial derivatives, derivative with respect to each of the parameters, and then equate them all to 0. Now, the funny thing, again, as I said last time, is here in this part of the lecture, we are somehow trying to look for closed form solutions for the parameters. Whereas in the entire earlier part of multi-layer neural networks, you are computing parameters just incrementally by backpropagation. That will work here too. It is just that here you also happen to have closed form solutions. You guys get that? Okay. So anyway, it's kind of interesting to see that the likelihood here would be a lot more complex function. So for example, here, if you have the probability that the flavor is cherry while the wrapper is green, given this network, is flavor being cherry will be theta times wrapper being green is wrapper being green when the flavor is cherry. Flavor is cherry, wrapper is red with theta 1 probability. So 1 minus theta 1 probability would be the green. You understand what I'm saying? In general, you should at least remember that given a Bayes network, you can compute the probability of any joint entry by just multiplying the numbers in the Bayes network. That's what we did before. Remember, we went from Bayes network to the joint probability you can always do by essentially, if you have a Bayes network on 5 variables, A, B, C, D, E, and I want, tell me the probability that A is true, B is false, C is true, D is false, E is true. I can just compute that by multiplying the numbers that are directly available in the Bayes network. When you have complete data, that's exactly what you're doing. Because each data point is completely specified. You know its attributes for all the observable, all the attributes are observable and you know their value. So for each data point, it will be something like this, theta times 1 minus theta 1 or 1 minus theta times theta 2, etc., etc. And you multiply all of them, you will get a more complex expression, which basically says the number of cherry candies, theta power number of cherry candies. If you simplify that entire multiplication, then 1 minus theta times the number of lime candies times theta 1 times the number of cherry candies in red wrapper times 1 minus theta 1 times number of cherry candies in green wrapper times theta 2 power RL, which is the number of lime candies in red wrapper, times 1 minus theta 2 times number of lime candies in the green wrapper. This is your expression. You take the log of it, then you will get that. And then you can take partial derivatives of that expression with respect to theta, theta 1, theta 2. And they will all basically give you, 3 expressions. You equate all those 3 expressions to 0 to get the stationary points of this function. And hope that what you got, in general, basically what they do is equate to 0, and whatever is the solution they expect is maximum. Okay, but really you should be making sure also that you take the second order derivative test and check its maximum value. Okay, so anyway, the interesting thing is, again here, if I have 3 equations in terms of 3 unknowns, it's not easy to solve them normally. It's only the easiest case is the kind of case here where each of the equation only names one unknown. Look at that. Each of the equations only names one of the parameters. So each equation just gives the one parameter directly. That's the best way of solving simultaneous equations. The second best is you have simultaneous linear equations, where individual equations might have more than one parameter, but all the equations are linear. The third is the end of the world, which is a whole bunch of simultaneous nonlinear equations. At which point you'll say, I don't know what to do. And then we'll just basically give it to gradient descent to find a good point. In a weird way, you're coming to this having actually done the more general solution. In the old days, basically, we will be looking at this and thinking as if it's a problem that we can solve, it should be having an analytical solution. Now we just say, if it happens to have an analytical solution, we'll take it. But if not, we'll just give it to one of these numeric methods like the gradient descent or gradient descent. Okay. And in fact, the easiest cases where this happens are actually the 2 cases that we just saw, which is any Bayes network which has tabular conditional probabilities, and you have complete data. That means each data point is described in terms of all the attributes. Essentially, this case happens, which essentially means you don't have to go through these points at all. You can just directly write each parameter in terms of the counts. Okay. So in fact, to point that out, it will work for these 2. This is the old Perl network that you guys remember. So imagine the data for this would be, the complete data for Perl network would have to be like this. Each data point should say the value for each of the 5 variables. So you observed. So one particular day you went and you found the burglary is true, earthquake is true, alarm is false, John calling is true, Mary calling is false. That's one sample. Another day you went and you found this sample. Notice that in all of these samples, every one of the variables has the value. That's what it means to say complete data. Complete data basically means each data point is completely described. For example, if you just went and found that burglary is true and John calling is true, but I didn't see the other things. I don't know the values of the other things. That would be incomplete data. Then you no longer can use the simple things that we did, because why? Because the missing variables have to be marginalized. And this is the other thing many of you like. Marginalization includes integration. In the case of discrete, marginalization includes summation. Logarithms hate sums. Logarithms love products. Do you understand what I'm saying? If you have summation, this nice simple way of doing equation solution won't work. That's actually what happens in the expectation maximization algorithm that we won't have too much time to talk about. Okay. So, and finding, if I give you a bunch of data like this, then if I ever needed to compute, any of the CPT entries. So for example, I will need here the entry alarm true. What is the probability of Mary calling given alarm true? And what is the probability of Mary calling when given alarm false? Those are the 2 numbers you would need there. And similarly, you will need for John given alarm and John given not alarm. If I want the John given alarm, I just take all the number of data points where John and alarm are both true, divided by the total number of data points where just alarm is true. That would be the conditional probability. You see what I'm saying? So again, this is what you would have done if you didn't do any calculus. But it turns out calculus tells you this is right thing. Okay. In all these cases up until now, we assumed that the Bayes network topology is given and the data is complete. Next, I'll look at the case where the data is complete, but the topology is not given. So I don't know how the Bayes network looks, but I do have the complete data. That means for every data point, for all the variables, values for the data point are given. That gets you to naive Bayes classifier, which is probably the last idea that I get to go slowly enough that you'll remember in class. So the naive Bayes classifier essentially says, so suppose you have data like this. This one is actually from the textbook. This is Russell's restaurant waiting habits. So for each of these examples, he has a whole bunch of attributes. Is there an alternative for the restaurant? Is there a bar at the restaurant, etc., etc.? And what is the estimated wait time? And then the decision is, will he wait for a table or not? And since we have nothing better to do in life, we are interested in predicting whether or not Russell will wait at a restaurant or not. I mean, these days, of course, this problem doesn't even make any sense because Russell is in Bay Area where probably all the restaurants are closed and there's not much hope going on there. But at one time when he wrote this, that was the case, right? Russell, by the way, stored Russell, the textbook on. So I want to basically, this is a classification problem. And given a new scenario, having seen these 12 examples, given a new scenario where there is yes, no, blah, blah, blah for each of these attributes, I need to predict whether he will wait or not. Okay. I can think of this as a Bayes network learning problem. Except I do have complete data. But what I'm missing is the topology. What if I just decide to make up a topology? Right? So what I'll do is, this is basically, this is Jean Harlow, an Hollywood actress, who is apparently said to have said, whatever you get me for Christmas, don't get me a book, because I have a book. Okay. I don't know if you guys will find this funny, because their books are the things that people used to read. A book is like, anyway. So the point being that you are asking, Jean Harlow of Bayes networks would be, don't give me a topology. I already have a topology. And the topology I'll always go with is this topology, which is the class causes the attributes. It's possible, right? Because every classification problem has the class and the attributes. So you say that Bayes network topology will always be class causing attributes. If I did this, then I'm done. Because I've now converted this into the problems that I've seen earlier, which is known topology complete data problems, where every one of the conditional probabilities are just ratios. You see what I'm saying? So in particular, if you basically have this network and this is your data, you can compute each of these probabilities. So for example, you would need will weight, probability, because will weight is it needs the prior probability in the Bayes network. So probability of will weight would be, consider all the number of times, the total number of examples are 12, and 6 of them he actually weighted. So 6 over 12 is will weight probability. Similarly, if I want patterns is full given will weight equal to S, which is one of the conditional probabilities I will make. So I will count the number of rows in which will weight is S, which is 6. And of those rows, I see how many rows have patterns equal to full. That happens to be 2. 2 by 6, a third. This is learning. This is machine learning. And as I said, back in 2006 timeframe, this was like what? Even now people use this, including logistic regression and naive-Bayes classifier. They are like the simplest machine learning techniques that you should always try first. And in fact, as I said, Peter Narvik, the second author of the book, said that Google just uses naive-Bayes classifier by default back in 2006. About the only thing, of course, is sometimes because you only have so much data, 12 data points, it's possible that the number of will weights is 6 and none of the will weight rows have patterns equal to 4. So you will wind up saying the probability is 0 by 6. You should remember from last class how bad zeros are in probability. You see what I'm saying? Because you throw in a 0, you will stay at 0. So they're basically, naive-Bayes classifiers have a trick of adding something to the denominator, adding something to the numerator, so that it'll never be 0. And that's called Laplacian smoothing. And this can actually be thought of as the Cromwell's rule, where Cromwell basically was saying the same thing in a much more flowery language that I was telling you yesterday, and day before yesterday, that I beseech you in the bowels of Christ, think it is possible that you might be mistaken. That means allow for every hypothesis to have non-zero probability. Similarly here, allow for every parameters to have non-zero probability. And the way you do this, and in fact, again, this winds up being needed in the naive-Bayes classifier because you're doing maximum likelihood rather than Bayesian learning. And so what actually winds up being the change that you do, for the naive-Bayes classifier for the same counts, is you, in addition to the 12 samples you have, you assume you have M virtual samples that you have never actually been provided, but you assume that you have M virtual samples. So the virtual samples M will be added to the denominator. And then for every attribute taking a certain value, assume that it will take that value uniformly. Okay. So then if there are M samples and you want to find the number of those samples where a particular attribute has value V1, you multiply M by P, P being the probability that that attribute takes that value. And this probability, you could have just initialized it to be a uniform probability. So if this variable has 5 values, then you can assume that it will take each of the values with 1/5 probability. The moment you do this, in essence, what happens is before you saw the first example, you have already seen M virtual examples. And this ensures that nothing becomes 0. And furthermore, when the data becomes larger and larger, that means you see more and more and more, restaurant scenario experiences of Russell, this M will be much smaller than the total number of data points. And the M times P will also be much smaller than the number of data points where that attribute has that value. So this initialization factor goes away. You guys see that? This is called Laplacian smoothing, and it actually makes complete sense based on the Bayesian learning, which we should be doing, but we are not doing. And so instead you come in and say, we'll do this small repair at the end. And if you do this, naive classifier works. Yes, go ahead.
So in the red equation, we're has the term number Ci A times God. Should it be?
No. Number of Ci is the number of elements in the class Ci.
Yeah.
Yeah.
But should it be Vj, not Vi?
You could do that. Yeah, I'm sorry. Yeah, you're right. AI can have Vi1. So AI can be taking values Vi1, Vi2, Vi3, etc. And you basically take that.
They're not necessarily equal, but they can.
Yeah, you typically, if you don't know anything else, you just assume they're equal.
Okay.
If not, you're making a prior probability as to how the attribute take different values. Yes.
So is this idea, is this kind of a similar idea to like the moving average stuff that we were doing earlier this semester, where we assume like if we don't know how to.
Kind of, because this one essentially you're initializing. It's actually much more similar to the PHI idea. Remember in the last class we said we are going to, the map essentially tries to maximize, find the hypothesis that maximizes P d given HI times PHI. So if you're maximizing the log, it will be log of P d given HI plus log of PHI. As the data keeps increasing, this piece becomes bigger than PHI. So in the limit, Bayesian learning is the same as maximum likelihood learning. Map learning is same as maximum likelihood learning. But for small number of samples, which is where MLE, which is where maximum likelihood is a bad idea, you're trying to put some crutches and saying, making sure that nothing becomes 0. Again, people will just come to naive Bayes and say, we do this. You know why we are doing this, because it actually makes sense given all the discussion we had about why setting probabilities to be 0 is such a bad idea. Because that means you're saying certain hypothesis has 0 probability. Now, one of the strangest things is naive Bayes classifier works so well that for a while people were writing papers on why does naive Bayes classifier work. Clearly, the actual Bayes network underlying these examples would not be that at all. This is what you just decided. It's almost like saying you've given a bunch of points. The first thing you do is try to put a line through it. Why did you put a line through it? Okay. So naive Bayes classifier turns out to be sort of like a linearity assumption for probabilistic reasoning. It actually gives, if you think in terms of what naive Bayes classifier gives as the posterior probability, that means after seeing a bunch of data points, Now, if you see a data point, you can give a posterior probability of its class, right? That's the prediction. The posterior probability prediction might be completely off. So in particular, let's say the real posterior probability prediction for a particular Russell experience, will weight, won't weight, will weight is 0.99 and won't weight is 0.01. Those are the real probabilities. Naive Bayes might actually say 0.51 and 0.49. 0.5 and 0.49 as a distribution is hugely different from 0.99, 0.01. But if you ask for the winner, in both cases, the winner is the same. Will weight is the winner. So that is what people have basically come up with as an reason as to why naive Bayes seems to work paradoxically. Because most of the time you are not really using the posterior, you're just figuring out who the winner is. Okay. And in the next 5 minutes, I want to, if you don't actually know the topology, you can also try the different topologies. That's the other way. As I mentioned, one problem with that is as you keep increasing the number of links in the network, the data likelihood with respect to that network can only increase. It can't reduce. So you need to add some complexity factor in terms of the number of edges that are there in the network. So if you are doing structural topology learning, you really do have to use map. ML, maximum likelihood, just won't work. The map basically says hypotheses with more edges are less likely. So it's making an assumption on the prior on the hypothesis. And then you can optimize. Okay. The last thing before last thing before we go off, and this will be setting you up for a longer lecture that I hope you'll watch. That I'll still show you about expectation maximization. But that's basically for incomplete data. Okay. So here is the mind-bending thing, right? Suppose I gave you this data. This is the Russell data. I gave you this data, which it's complete. In particular, in terms of the classification terminology, in the probability terminology, you talk about complete versus not complete. Complete means all attributes have values. Not complete means some attribute at least doesn't have a value. In terms of a classification, you talk about labeled and unlabeled. You guys heard this part, because in fact, most of the people who are saying they're doing AI work are doing junk work for various Silicon Valley companies like Crowdflower, etc., where they look at a picture and say, oh, there is a dog here, there's a cat here, there is a woman crossing the road with a dog. I'm doing AI, mom, is what you tell them, but no, really, this is what you're doing. You're essentially annotating images. So you're providing labels. Okay, so I have the labeled data here. This is the amount of data I have, but I somehow found some more Russell examples. They were like, outside in the back door. You know that the more the examples, the better the learning. By the way, there was some person somehow made a fatal misunderstanding that if you increase the number of examples, the learning suffers. That never happens. If you increase the number of parameters, there was this worry that learning can suffer because of overfitting. The more data, the better learning. You cannot yell at data. It makes no sense. The reason I don't want to give you data because I'm lazy. I don't want to give too many examples. I just hope that you can learn from 1 or 2 examples. But if there are people giving you examples, you're happy to take them. You as a student who have no other life, you do more and more examples, you'll learn the concept better. So in this particular case, I have these examples with the labels, and I have a bunch of other examples without labels. I want to give these to you. Would you like to take them? From a probabilistic sense, this part is complete data, this part is incomplete data. From a classification sense, this is labeled data, this is unlabeled data. On the web, oftentimes there's a bunch of labeled data, there's a huge amount of unlabeled data. Would you be interested in using the unlabeled data? First thing you have to actually understand that you might want to use unlabeled data. My example to make people understand why that is important is, remember in your math textbooks when you were in grade school, they would have tons and tons of exercises, unlike when you are in grad school or undergrad where they think 1 or 2 exercises is good enough. Tons and tons of exercises. And they'll have answers for them at the end of the book. One funny thing, most textbooks would only give answers to either the odd numbered or just the even number. Some really lazy textbook people will only give it for the prime numbered answers, even fewer answers. So the question is, why the heck do they take the time to write all these other problems when they don't give the answers? Should there be a version of the textbook where all the odd numbered problems are removed and would you like to buy it? What are the problems without answers doing for your learning? And the mind-blowing thing is not every random sequence of words is a problem. Coming up with a problem is actually hard. As a student, what you care about is what's the answer. The reason we don't want to give too many examples is coming up with problems is hard. Do you see what I'm saying? So unlabeled examples are like problems. These are real, naturally occurring problems whose answers have just been masked out. If it is that kind of a data, you should be able to exploit it and do better than just this much data. On the other hand, if this unlabeled data is randomly made up, that means I didn't actually, now that I know that you're a sucker, you're going to buy unlabeled data. Right? So before I actually found Russell's restaurant habits data with just one column masked and I sold it to you. Now that I found there's a market for this, I say, how the heck will you know whether this is real data or not for Russell? So I just make a whole bunch of, any number of these examples and I sell it to you. You being a bozo will buy it because you thought the previous one was working. Why won't this one? That won't help. That's like basically Russell's restaurant habits have a pattern, just as problems have a pattern. Not every random sequence of words is a problem. You understand what I'm saying? Okay. So unlabeled data is actually very useful and many powerful machine learning methods use unlabeled data to improve their performance. And I'll tell you one mind-blowing idea that you can do just yourself for this problem. And that is actually the simplest example of expectation maximization. Okay. So the idea there is, remember, you have this stuff which is complete. You can apply a naive-based classifier here. That means you can learn a naive-based classifier here. Yes, because I just told you how to do it. Now that you have a naive-based classifier, you can predict the labels for this. Yes. Now, rather than just take the winner, even though I said the posterior is actually bozo and only the winner makes sense, if it says this is 0.51, yes, 0.49, no, then you will say this is a 0.51 example for yes. And this is a 0.49 example for no. When did you see this kind of a thing before? Fractional examples. Likelihood weighting. You see what I'm saying? So I just use this naive-based classifier to predict these guys' posterior probabilities. So these posteriors are 1 and 0, or 0, 1. These can be 0.49, 0.51, 0.52, 0.48, etc. So these are a bunch of fractional examples. Now, since it's late in the day and you seem to take anything I say for granted, I'll say, now you have more examples. Redo naive-Bayes classifier for all these examples. So you have fractional examples as well as the normal examples. You compute a new naive-Bayes classifier. Still not giving up. I'll say then, now that you have a new naive-Bayes classifier, repredict these guys' values. You get new fractional labels. Compute a new naive-Bayes classifier. Keep doing this until you feel sick of doing this. Then the last naive-Bayes classifier you have would be better than the one you just learned. In particular, this is basically what this picture is saying. It's written in whatever I said. And in particular, you will see that if I give you unlabeled examples, okay, this is the algorithm that is using the unlabeled examples. This is the one which is using only the labeled examples, where the number of labeled examples keep increasing. In the beginning, you notice there's a huge difference in accuracy. Of course, as the number of labeled examples become infinite or something infinite plus another 15 is still infinite. So it becomes close to each other in the end. This can be also called semi-supervised learning. Supervised learning means you have data with labels. Unsupervised learning means you have data, no labels. Semi-supervised learning means you have data, some have labels, some don't have labels. And I told you how to do this. This turns out is a special case, not even the full, special case of expectation maximization algorithm. So in the case of expectation maximization algorithm, some particular variable will always be absent. Like fully absent, it's unobservable. So you never seen it. It's not that for some they has labels, some there are no labels. This variable just never had a value. The beauty of the approach that I told you is if you don't have any values, you just initialize some probabilities and do this, you will still do. And why should I stop there? And it turns out that actually this idea, and this is all advertisement to make you hopefully see the EM lecture that I don't have time to teach here. But for example, things like, hidden Markov models, learning hidden Markov models involves expectation maximization algorithms. Learning, there was a time when this class would have some grad students, some undergrad students, and there are marks from both groups. And I need to figure out, if I got the marks without knowing whether the person was a grad or undergrad student, can I nicely cluster them into these are the grad student marks, these are the undergrad student marks, so that I can, for example, hopefully apply different thresholds. These are called Gaussian mixture models. That is also expectation maximization. Okay. And then, I don't know why I should show this, but I just want to say that obviously, again, if you see the lecture, you'll see me explaining that this crazy thing that EM is doing when you are learning the parameters of the naive-Bayes classifier, that's called maximization step, because you're doing likelihood maximization. When you're using the current naive-Bayes classifier to predict the variable, the label, that's called the expectation step, because you are actually expecting based on the current hypothesis what the labels are. And if you do this expectation maximization, somehow you seem to be improving the quality of the learner. And the reason it turns out is there is some kind of a likelihood function onto which you're trying to climb. And rather than do simple gradient ascent, you will essentially find a lower bound on this function, which happens to be the same as this function at that point. And if you have such a lower bound, then when this becomes maximum, when this function becomes maximum, that would be a big step towards the maximum of the real function. So you can think of expectation maximization as a customized step, gradient ascent. Okay, fine. So I only have 5 minutes to kind of try and end the class. So I will go even faster on this because I'm sure the next class is ready. So these are the topics that I said I will cover in the chapters in the textbook. If you look at the textbook, the ones in green, I think I covered most of it. The ones in sort of red, I did not as much. The ones in brown, I covered partially. But the textbook is really huge, but you kind of have a sense where we went with that. I know that you are not in the best of moods. It's the end of the course, you do too much work, all that stuff. But as much as you think you do a lot of work, making you do a lot of work is a lot of work for us. Okay, it's just so much simpler to say, watch somebody else's videos and take this true-false test and then let the machine give you the grade. Okay, but it turns out that making a course demanding requires a lot of help. And as I said, I have had very good help. I mean, Siddhant, who is sitting here, Karthik, who is not here. Karthik actually kind of was making sure that he will answer all your questions. He was ensuring that the exams and projects are set up. Siddhant and Karthik were holding the office hours. Abhiram, is Abhiram here today? He's not here today. He was the grader. It turns out actually that this guy is the only guy that your tuition dollars paid for. That's it. These two guys I am paying. Of course, your tax dollars, your parents' tax dollars are paid because they gave money to NSF, DARPA, etc. I get grants, and then I ask these guys, in addition to research, help these guys. Do you understand what I'm saying? So realize that it's hard to make you work hard. Okay. So honestly, if it was just Abhiram or even less number of grading, the course would have been much simpler. Seriously, because you would have had so many exams, you wouldn't have had all this torture that you had to go through. So if you are really unhappy about this, you know who to blame, not me. Okay. And then, of course, as I said, much of my students also keep becoming part of my venting anytime I'm doing the course, and they're pretty unhappy because I spend too much of the time. The entire mornings just are gone, and then in evenings are gone trying to change the piazza. Whether you appreciate it or not, that winds up being, unfortunately, the truth. So they are happy that the course is over. Next semester, I won't be teaching. Piazza, by the way, that's the red, and there is a red and a blue line, you can't see it. That's because the TAs were not sleeping. You ask a question, the answer will be there. And you guys got used to this. I've seen you ask questions at late times, and they would still be answered. Okay. And then these basically kind of tells you, how much of a time they were spending in terms of the number of answers that they were giving, etc. I had no work, of course, I was doing this stuff, but so were the other people. Okay. Actually, let's see, there was this other thing. There was actually, I should remember that. These, by the way, Dennis, stand up, Nicholas, Michael, Rachur, Joshua. Thank you for taking part in Piazza. You apparently wrote, I know Dennis more or less wrote most of the notes, and I thought there was these other people writing the notes, and then he told me that he was controlling the other people to write the notes. Thank you. So there were, taking things seriously is important. That's the only reason. There were course reflections that you did. I don't have time to go through this whole thing, but essentially, the stick behind making you think about what happened in the course is, if you remember, if any of you know 36 questions to fall in love by, I was doing that for you. So even if you thought you hated this course, after you answered those 11 questions, you might start loving it. Okay. So that's what you did, and there were very interesting answers. I don't actually have time to this. I did go through all your answers and made some points about it, and I put up that as a top of thing. But those were the word clouds from your answers. This one was about what you found interesting. This one about technical details. This one about ideas that transcend AI. This one about jokes. Apparently, Watson was big for many of you. And this was the wish list. And unfortunately, you can't see this, it's all black. But so one of the things that people were very interested in is the ethics. And some other people were interested in deep fakes. I'll send you a link on my general lectures, not for the class, on both AI ethics as well as deep fakes. And you are welcome to watch them. At least you'll be in the same annoying voice instead of getting some other annoying voice. Okay? So that's that. The staring part actually is part of the people who know the 36 questions to fall in love by. Is their last very important part, which is after all these questions, you're supposed to stare at each other. And so I did consider having you come to my office and stare at me, but there are differently rules against it. So I am hoping that you will stare at the true and false questions as well as the exam that I'll be giving you and make up for that way. And also, please consider doing the full term evaluations. Currently, I think it's about 39%. I would really like to get 100% of people participating. Okay. The last thing, if this works, it would be great. Okay. I mentioned Schindler multiple times. So this is the last Schindler. The question of how many topics time, and you wanted to hear some various topics. These are the ones that I would have liked to cover. Handling partial observability is the idea that I can really get to. So bounding trees and HMMs. Handling time, planning dynamic-based networks, different networks that we create. Human area is something that I do as my research, multi-agent, where X research, learning, stuff to do. And then, of course, I would have probably, if I had more time, less demanding more often. So I'll be kidding. I'm sure I would have found more topics. So those are sort of the important topics that I think I had more classes. Those are the ones I would have done. The rest of it is anyway. So part of the other things, that I want to say, my day of peak was telling you they asked me what is the time. Like it or not, that's what we got out of this. I do this because it's a senior level course, it's a failure, unless it tags you to the edge of the node. Very, very right side of it. Center of contrast. So you will remember this course. Very last thing I want to say is and with understanding many of you hopefully you know what's actually there. Another book. Many of you hopefully not that different. But so I am told that this is the union as us. And so, anyway, thank you. Good having you.